Czyli odwrotnie? Trójka, czwórka można... A to był kanał polski testowany. Mówiła pani kanał polski. Kanał polski bym poprosił. Poprosiłbym jeszcze kanał polski. Już, moment. Ogarniemy tę symultaikę. Możemy jeszcze kanał polski spróbować dla... Masz kanał polski?
Teraz mówisz do mnie w kanale angielskim.
Teraz powinienem mówić 2 kanałami.
A daj mi tu po angielsku.
Raz. No i tym samym powinno wchodzić też Znaczy, tym samym też powinna wchodzić symultaika angielska.
Dobra.
Mamy miliardy metrów sześciennych gazu. Stale rozwijamy się, budując tysiące kilometrów nowych gazociągów. Współtworzymy zintegrowane systemy przesyłowe w Europie, dzięki takim projektom jak dwukierunkowy gazociąg łączący Polskę i Danię, korytarz północ-południe czy interkonektory. Będąc filarem bezpieczeństwa energetycznego kraju i regionu, rozwijamy inwestycje umożliwiające dostawy gazu z nowych źródeł i kierunków. Rozbudowujemy terminal LNG w Świnoujściu Jesteśmy też odpowiedzialni za powstanie terminalu pływającego w Zatoce Gdańskiej. Zatrudniamy ponad 3000 pracowników, których łączy pasja i profesjonalizm w dostarczaniu czystej, konkurencyjnej cenowo i stabilnej energii. Dążymy do zrównoważonego rozwoju, wspierając lokalne społeczności i chroniąc środowisko. A ponad wszystko zmieniamy oblicze polskiego gazownictwa oraz integrujemy rynek gazu w Europie. Gaz System. System, który łączy.
Polska Spółka Gazownictwa to największa spółka grupy kapitałowej PGNiG. Jako narodowy operator systemu dystrybucyjnego i europejski lider tej branży, przez prawie 200 000 kilometrów gazociągów codziennie dostarczamy gaz do ponad 7 milionów odbiorców. Stale czuwamy nad bezpieczeństwem i ciągłością jego dostaw. Chcemy, by z błękitnego paliwa korzystało jeszcze więcej mieszkańców Polski, dlatego realizujemy strategiczny program rozbudowy infrastruktury dystrybucyjnej.
Inwestujemy w tworzenie nowych gazociągów, rozwijamy nowoczesne technologie i podnosimy efektywność podejmowanych działań.
Stawiamy także na gazyfikację wyspową. Dzięki stacjom regazyfikacji skroplonego gazu LNG zapewniamy szybki i bezpieczny dostęp do tego paliwa tam, gdzie go wcześniej nie było. Dzięki naszym działaniom wzrasta liczba odbiorców gazu, a proces przyłączenia do sieci dystrybucyjnej PSG jest łatwiejszy niż kiedykolwiek wcześniej.
Wystarczy zgłosić się do jednego z prawie 200 miejsc obsługi klienta w całym kraju lub skorzystać z internetowego portalu przyłączeniowego.
Polska Spółka Gazownictwa. Dostarczamy paliwo gazowe w sposób ciągły, bezpieczny, z poszanowaniem środowiska naturalnego. Polska Spółka Gazownictwa. Wybieram gaz. Polska Spółka Gazownictwa. Dostarczamy paliwo gazowe w sposób ciągły, bezpieczny, z poszanowaniem środowiska.
Są też wykłady hybrydowe.
Energy gives power. Telecommunications gives connection. Banking gives stability. Big data gives knowledge. Smart city gives new possibilities. Healthcare gives strength. Insurance gives safety. Administration gives support. Defense gives security. IT gives freedom. ASECO. Technology for business, solutions for people.
Raz, dwa, trzy. Drugi. Raz, dwa, trzy. Raz, dwa, trzy, jeden, dwa, test. Raz. Coś tak. Właśnie też. Raz, dwa, trzy. Raz, dwa, trzy, raz. Raz, dwa, trzy. Raz, dwa, trzy. Trzy, raz, dwa, trzy. Raz, dwa, trzy. Raz. Raz, dwa, trzy, jeden, dwa, testy.
Dzień dobry Państwu, witam wszystkich na drugim dniu szóstej konferencji naukowej Bezpieczeństwo energetyczne, filary i perspektywy rozwoju, która tradycyjnie odbywa się w Rzeszowie, nietradycyjnie we wrześniu. Proszę Państwa, czasem bardzo przypadkowe decyzje mają daleko idące konsekwencje. Postanowiłem dzisiaj wcześniej opuścić hotel i przyjść pogadać z przyjaciółmi, a zostałem wyznaczony na moderatora panelu. I to chyba pierwszy przypadek, kiedy politolog moderuje panel o kwantach. Moja styczność z kwantami jest bardzo ograniczona, lubię czytać science fiction. I to właściwie wszystko, co wiem o kwantach. I wiem też, że każdy autor inaczej to opisuje. I nawet słyszałem stwierdzenie napęd Alcubierra. Nie wiem, czy to ma związek z kwantami, czy nie, ale być może. Proszę Państwa, w związku z tym będę moderatorem bezinwazyjnym pod względem merytorycznym, a wyjątkowo inwazyjnym pod względem czasowym. W końcu się muszę jakoś wykazać, prawda? Mamy to szczęście, że wszyscy uczestnicy tego panelu znajdują się tutaj razem z nami w sali. W związku z tym, nie przedłużając, chciałem oddać głos panu doktorowi Pawłowi Kwaśnickiemu z ML System SA, który będzie mówił o fotowoltaice XXI wieku w oparciu o struktury niskowymiarowe.
Bardzo dziękuję.
Thank you very
Co to
much.
znaczy, to mam
And what
nadzieję, że
it means, I hope will become clear in a
Tak,
moment.
żeby politolog zrozumiał, dobrze?
Please
Postaram się w trakcie tej
present it so
prezentacji.
that even a political scientist can understand this. I
Jeżeli
will
mówimy
try
o
during this
fotowoltaice,
presentation.
to
So,
bardzo często myślimy o takich
when we
klasycznych
think of
rozwiązaniach,
photovoltaics, we most
które
often
możemy
think of
widzieć w życiu
traditional
codziennym w
solutions that we
postaci
see
paneli fotowoltaicznych
on an everyday
zamontowanych
basis,
na
that is
dachach czy
photovoltaic panels installed on the roofs or in front of buildings.
Niemniej jednak
But
w tej prezentacji
in
chciałbym
this presentation, I want
przedstawić
to
wizję
present a
fotowoltaiki
vision of
XXI wieku.
photovoltaics of the
To znaczy to
21st century and what this 21st century photovoltaics will consist in the future is increasing conversion, so getting more energy yield, improving the operation stability, so the ability to generate stable energy yields regardless of the angle at which the light falls, the insulation, and so on. The ability to combine photovoltaic systems with other energy systems and energy storage systems, and finally the ability to install in different places.
Zainstalowanych na dachach bądź
So far, most of us are used to photovoltaic modules installed on the roofs or in front of buildings, which are non-transparent and which have very limited, and with the ability to use them in other places in buildings is very restricted. Whereas examples of a new type of photovoltaics, which is already present on the market and which is integrated with construction, the majority of them are installations and products of ML systems in this kind of photovoltaics, and this is what our company specializes in. So here you've got a photovoltaic facade, a photovoltaic lamp, which can be completely off-grid. We have skylights, which are photovoltaic skylights. Apart from generating power, they also provide some light because they are transparent to some extent. But the things you see here are based on photovoltaic systems which are already well established on the market, and it's based on silicon. And this is
rozpopularyzowana
the most
i charakteryzuje się
photovoltaic
największą czy najszerszą obecnością na świecie. A kto jest głównym producentem takiej właśnie fotowoltaiki? Możecie Państwo zobaczyć na pierwszym wykresie. Otóż prym wiedzie oczywiście, czy wiodą oczywiście
So of course the leaders are Asian countries. Some are produced in Europe and in North America, but the rest of the world is very much behind. And with regards to where photovoltaic systems are installed, Asia, mainly China, are a leader, and we are somewhere far, far behind it, behind other European countries and and North American countries, but you can see that this trend is growing. So there are more and more systems installed, and more traditional photovoltaic solutions are produced. What do I mean by traditional photovoltaics? Photovoltaics based on silicon, but in this category we can already distinguish different generations or technologies of those photovoltaics. So over the last 20 years, this is how these technologies competed. So around the year 2010, it seemed that multi-crystalline silica would be the dominant photovoltaic technology, but as you can see right now, monocrystallic silicon cells are the leading ones, mainly because of the improvement in the quality of the base material, that is silicone, the improvement in the processes of doping the silicone, and finally improving the purity of the process of producing silicone cells, and this caused the monocrystalline silicone to become leaders. They have more than 20% efficiency now. Why should we be talking about photovoltaics at all? Well, we are trying to cover the energy demand of the world, and according to World Energy Assessments, the annual requirement of the world for energy is estimated at about 5,600 exajoules. Solar energy potential is almost 4 million exajoules. So this potential, the potential of solar energy can easily cover the demand of the whole world for energy, even if we use only a small proportion of this potential. So this is why photovoltaics seems to be the ideal solution. And right now, 3 or 4 generations of photovoltaics are distinguished. The first one, most popular, is based on silicone. The second is based on thin layers. So those are cadmium 6 CGS or amorphous silica panels. The third generation of photovoltaics doesn't have a PN junction, and those are organic PSC, QDSC or DSCC, and the ones with quantum dots. Why do we distinguish those? Because in photovoltaics it's important to improve its efficiency, reduce the operating cost, and this is what you see on the graph below. So you see those 3 aspects here. Every next generation, while keeping the same cost or reducing the cost of production and the cost of operation, is to ensure higher efficiency and improve application possibilities. One of the ways to cut the cost of producing photovoltaic cells is to reduce the amount of material that is consumed. You can do this by decreasing the thickness of the cell or the materials used as active materials for the conversion, and in recent years we have seen the direction in which photovoltaics are moving, which are to reduce the thickness of those materials from standard crystalline silica, which is several hundred micrometers, through amorphous silicone, then cells which have just a few micrometers of gallium, and then those based on indium selenide or iron sulfide, where there are tens of micrometers, and then you get ones with just a few nanometers. So this thinning of cells has also been observed for standard silicone cells. This thickness has decreased from almost 0.5 millimeter to 200 or 180 micrometers, and at this thickness it has stayed for silicone cells, and you don't see much of an opportunity to improve this. So it seems that the right direction is to look for new materials, and those new materials could be quantum dots. The global trend of quantum dots in terms of the work on this material is shown on this map, which shows where you see the greatest interest in nanomaterials, and in particular quantum dots, which belong to this group. So until June of this year, over 14,000 articles have been published about the use of quantum dots in photovoltaic cells, and you can see that both the scientific community and the industry are very interested in using quantum dots for producing new types of photovoltaic cells. So what are quantum dots? They are nanocrystals of semiconductors whose diameter is of several or between 10 and 20 nanometers. It may reach to 100 nanometers. But what is important is that the energy gap in those materials is greatly dependent on the geometry of this material and its size. So by controlling the diameter of the quantum dots, you can control the energy gap. And in addition, in those dots, you can see you are multiplying exciton generation, which can greatly improve the output of cells based on those materials. And what is more, those quantum dots are now cheap and easy to produce. What's important about quantum dots is that the electrons are located in the energy zone, energy space. So this makes it possible for us to effectively build the device, which is the photovoltaic cell, which is sensitive to a specific length of the electromagnetic wave. So they can be used not only for photovoltaic cells, but also for transistors, for lasers, for quantum computing, and for many years they have been used for medical imaging as markers. So how does a photovoltaic cell based on quantum dots work? Well, it works very similarly to a traditional silicone cell. So what is important is absorption. That is the state at which the photon is absorbed by the active layer. Generation of the electron hole pair. This is the exciton, and then you separate the exciton into electron and hole, and the collecting layer collecting the charges. What is very important is that when you build a photovoltaic cell based on quantum dots, you can change the range of absorption, so the length of wave which is absorbed by the cell, by selecting quantum dots of the right size. And the graph that you can see here shows you the change of the value of the energy gap as a function of the radius of the quantum dot. The greater the quantum dot radius, so the bigger the dot, the longer the wave that this material can absorb. Longer waves mean lower energy. Building a the design of a photovoltaic cell based on quantum dots can be very easy. Of course, this is great simplification because you need very special technology for it, but what is very important are 4 elements. So you need the photoanode on which the quantum dots are located, and the counter electrode, and the collecting electrodes. So the first work on quantum dots, which started over a dozen years ago, were based on DSSC cells in which electrolyte and dye were used, and in that cell the dye was replaced with quantum dots in order to get higher efficiencies of conversion and greater stabilities. But in reality, all photovoltaic cells, and in particular those from group 3, what is very important is the ability to obtain several effects. So using the down conversion effect, using the MEG effect, using the up conversion effect, which is using hot electrons or hot charges to generate electrical current. One aspect and major advantage of the use of quantum dots is that you can expand or broaden the absorption spectrum. By broadening absorption spectrum, we mean that they are able to absorb both UV, visible, and infrared radiation. So the traditional silicon cells effectively absorb the visible light, but they do not absorb any infrared because of the energy gap of silicon, and the ultraviolet range actually is negative for that operation of that cell, and actually is good if ultraviolet does not reach the surface of silicon. The use of up and down conversion, that is changing the length of the wave using, for example, quantum dots to a useful range, well, you can consider this in many ways. So first, you can directly absorb the ranges of higher and lower energy, and this can be done by using quantum dots as absorbers and converters. You can also use quantum dots as absorbers to convert the electromagnetic wave to the range which is effectively absorbed by other materials, other active materials in the photovoltaic system. So you can, for example, build a tandem cell in which the primary material that converts photons into electrons is silicon, but the infrared and ultraviolet ranges will be absorbed by quantum dots and then converted to the range that is effectively absorbed by the silicon material. Another interesting effect is the MEG effect, because since you are able to generate many electrons by absorbing one photon, you can actually have very high conversion outputs, even exceeding 100%. Our work at ML System on the technology of cells based on quantum dots started several years ago, but actually our experience gained building DSSC cells, some 10 years ago, helped us a lot. And this started with selecting the right substrate on which quantum dots are deposited, which quantum dots were first properly designed and then selected and synthesized. The next step was to select the right method of depositing those quantum dots, because please remember that those are objects that are nanometers in size. In the next step, which takes a lot of time, we optimize this, and now we have already gone through upscaling and optimizing this, and thus preparing a commercial line for producing solar cells based on quantum dots. Of course, the selection of quantum dots or selection of absorbers was complex in that there are very many different types of quantum dots that have different optoelectronic properties, and out of this broad group of materials we selected those that are the most beneficial in the early stage of producing photovoltaic cells. Of course, you want to select dots that not only give high energy yields but also are very stable, and mainly that they are easy to work with, so they can be deposited on the selected substrate. And the selection of the substrate was another important aspect that we needed to focus on. And there are important aspects like the absorption of quantum dots by the surface. so how those quantum dots are absorbed in the structure of the material, and also transferring the charge through the substrate, which is the photoanode, and the possibility to grow this photoanode on a conductive layer. So we started with structures that were very porous, in which the charge flow was very disturbed, and then we ended up with very uniform layers that can be easily grown on glass base. And when depositing quantum dots, an important barrier was how to characterize what has been placed on that selected substrate. So we're using nanometric objects, so any attempt to verify the regularity of the deposition process meant you had to use advanced equipment. So we had to buy high resolution scanning electron microscopes. We used traditional electron microscopes. We often used atomic force microscopes. So this allowed us to optimize deposition to such an extent that we can very precisely control both the thickness of the layer and its orientation, and the correction or the regularity of interfaces, so the connection between the quantum dot and the photoanode. And we have received something that we have obtained something that looks like ordinary glass pane, so thousands of hours, and you got a product which is supposed not to be different and isn't different from a standard glass pane. It is completely transparent in the visible light range, but it effectively absorbs infrared and ultraviolet, which range produces electricity. Of course, this is just the beginning of our road, because the opportunities for using quantum dots are much broader. Literature contains many publications about the ability to combine quantum dots with either silicon cells or multi-junction cells in order to improve energy yields. There are also studies which combine quantum dots with graphene layers, so where the graphene layer is the effective conductive layer, and all of this is to improve efficiency, and it is possible to reach efficiencies exceeding 35%, and so effectively absorbing a very broad range of the spectrum, operation at a very broad range of the angle at which the beam of electromagnetic radiation falls on it, and operating regardless of the temperature and other conditions, and finally cutting the cost of production so that those cells that we want to market be competitive in terms of price, and so that they could not only compete with but be complementary to the technologies that are already on the market now. Thank you for your attention.
Panu doktorowi.
Very much, doctor, and I hope that our exciting level, the level of our exciters emitted by our brains has increased, and I'm really glad that we managed to find the transdisciplinary approach. We are also talking about depositions, but we have some similarities between social sciences and the quantum theory. So it also turned out, as Dr. mentioned, this upgraded. I studied at physics. My math physics professor told me about the photons which were changing the color into red, so their wavelength is changed. So now we are talking still about photovoltaics, and though we increase our objects of research, because we are not talking about nanoparticles. So I would like to invite Professor Agnieszka Iwan from to tell about the fourth generation photovoltaics and solar chargers. It sounds fantastic. Ladies and gentlemen, I'm not sure if I can do it sitting, but I'll try. I'm really glad to be here, and I would like to thank Dr. Kwaśniewski and ML System Company for inviting me to this conference. It's my first time in Rzeszów and at this conference, so I'm really absorbing everything, both the scientific, academic aspects and other aspects. So I encourage you to move. We can measure your spin. Yes, thank you. I do not want to change the formula, the applicable formula. So yes, we will talk about it, and I will tell a bit about scientific aspects, and then we will move to practical solutions which we have developed in our institute in Wrocław, and of course some solutions with collaboration with other partners, domestic and foreign partners. And I wouldn't be myself if I would not refer to the conference, the energy security, and our military institute. So the relations between energy and security, you have it presented at this slide, and I have taken it from a paper by Johansson from 2013. We can present it in various ways, and here you can see it as a subject which is threatened by a security threat, and a security which generates insecurity or inconfidence. But apart from military security, we also have non-military security, which during peacetime is very important. And here we can tell a few types like energy security, environmental security, and cyber security. So I will tell you about my conclusion, which says that even during wartime, without energy security, we just nothing. I can remind you, blackout, this is key also during war times. And we all dream, everybody who deals with photovoltaics and energy storage and other forms of energy acquisitions, we all want to achieve this golden triangle in photovoltaics and energy storage. It is as we want to achieve a synergy between efficiency, stability, and price. And of course, it all will be environmentally friendly. And we are aware, being lecturers and teachers, that the environmental awareness is growing among young people. And we are also aware that the costs of building maintenance are increasing. And also this integrated photovoltaics integrated with construction is key. So how can we achieve it? So we must have a synergy between materials and their properties. As Dr. Kwaśniewski has mentioned, and I presented in a different way, we have 4 generations of solar cells, and the 4th generations this is our organic photovoltaics with various plasmonic inclusions. And as you can see, this was born in 2010 as a consequence of solar cells of 3rd generation, which were insufficient, had insufficient efficiency. So the parameters, people tried to improve them, so they added nano inclusions, plasmonic nano inclusions. So you can see in this cloud, and I dealt with various plasmonic inclusions apart from quantum dots. So I hope that now, when I start collaborating with ML systems, it will change. And so I have asked my colleague for 5G, and this is the second part of my generation, because in the 21st century it is key not only to work on solar panels of various generations, which are not to compete with each other, but they should complement each other for various individual applications, but to integrate these these devices with energy storage. But before I move to this topic, I would like to tell you, and so when we are talking about third and fourth generations of cells, we have organic polymer DSSC cells, which are promoted by ML Systems, perovskite cells, well known because there's a boom in media, and we have so.
Każdy z tych rodzajów ogniw ma zarówno zalety, jak i wady, tak? Do zalet się przyzwyczajamy, traktujemy je jak coś normalnego, natomiast uwypuklamy wady i próbujemy z nimi walczyć. No, chcę Państwu powiedzieć, że najbardziej, że tak powiem, dalekie od zastosowań praktycznych
achieving the efficiency in the production scale. In the laboratory scales, we have records. So we have modifications of materials to obtain efficient cells and stable in the air atmospheres. So this colored cells are satisfactory efficiency, but the liquid electron is not really. So we are looking for solid or gel cells, and we also have a problem with long-term stability. So we're trying to find how to replace iodium with, for instance, cobalt, and a high price of ruthenium and platinum and perovskite cells. Well, advanced technology, which is in hybrid system connected to silicon cells, but there is always some but. The most efficient cells are lead-based, and scientists are trying to replace lead with other metals. The most efficient at a level of 30% are cells with rubidium instead of lead. So, and the stability in the air atmosphere. This is always a problem with perovskite cells because they deteriorate. So we are trying to encapsulate them. And there is the fourth generation of solar cells, nano particles, plasmonic nanoparticles. So this is just the application of plasmonic nanoparticles with a proper size and shape, which can improve efficiency of a solar panel, of a solar cell. But it's not so trivial, because we know there is a tendency to form agglomerates, and the success for this cell efficiency is affected not only by the shape and size of nanoparticles, of plasmonic nanoparticles, but the whole design of a solar cells, because as you certainly know, also the location of various of these nanoplasmonic particles with the same shape and size in the active layer can also affect the efficiency of a solar cell. And ladies and gentlemen, I also would like to tell you that we are talking about efficiency, and because when we go from the laboratory scale to commercial applications, efficiency for all generations of solar cells goes down. Why is that? Because we have a problem with obtaining large area solar cells, and there are also structural defects which diminish the efficiency. So for organic panels, it can be 17% in the laboratory scale, but it goes down by half for commercial applications. So we have quite a lot to do. And what do we do in our institute in VT? So we have various research. We research materials, organic and non-organic synthesis, hybrid compositions, and we deal with solar cells of various generations and energy storage. So we also produce them in a laboratory scale, especially lithium ionic batteries. So well, I would like to refer to our joint project with ML Systems, which have just been completed. So first about a gel electrolyte, which would replace liquid electrolyte. We have prepared such an electrolyte, and it was used in cells manufactured by the ML system with large and small cells, and it is successful because the efficiency is comparable with a commercial cell by a Swiss similar of this type from a Swiss company, but with a liquid electrode which can leak and reduce the photovoltaic parameters. I would also like to tell you about other material aspects. We have completed an international V4 Korea project. We have already know spirometa, which is an organic compound. Here it's at the bottom under this green, which is very expensive. Why it's so expensive? Because it's a multi-stage synthesis, and we use inorganic catalyzers. We have catalysts. We have proposed the synthesis without toxic solvents, only with an organic catalyst, so the cost is much lower than for Spiro, and the efficiency as the the absorption spectrum is the same as for Spiro, so it's stable for 7 months in a perovskite cell, and it does not show the hysteresis effect, which is also key for developing perovskite cells. I can boast that NCBR has invited us after completion of this project to show this in the success tab. And another solution, which is a material solution. This is our projects carried out together with Jagiellonian University, with Professor Marzec, where we are trying to develop biodegradable electrodes, where we add carbon nanotubes, single wall, and we research their mechanical properties and optical properties and electrical properties. And this is project, it's a doctoral thesis by Mr. Patrick. And what do we have in our institute? If you want to cover it, we have various measurement instruments for practical application. In particular, we are specialized in thermal vision camera, where we can easily and in a cheap way determine structural defects on the surface and the whole cells and equipment. So I invite you to collaboration. We have 3 methods. We have three devices for applying layers. So we have a few methods like by spraying or by rolling. So we also scale up technology and the whole set of equipment for making organic solar cells, and our solutions for solar chargers, which is most important. It's innovative in our country. So in our opinion, innovations are about looking for materials which combine properties of a few materials. And when we are creating these solutions, we had declared boundary conditions. And as you know, permutation, which is a change or replacement, conversion, as set, within this set, and practically these are, for instance, Lego bricks which can be adjusted so we can have a final product, and puzzles where each of these components of these bricks must fit. So our solutions are both scientific and implementary for both civil and military applications. So we have chargers from 6 to 9, and we go towards miniaturization of our devices, but we also manufacture large devices. So I have decided that each finished product has a product sheet. So this is a finished proposal for an interpreter. So it's not at a laboratory, it's our declaration. It can work and is applicable. And here is a classic example for which can be used, for instance, for charging cell phones. So the first generation of solar chargers was based on various solar panels and super capacitors as energy storage, and we also tried to make hybrid solar cells combined with silicon cells. We have a charger made with together with ML systems and super capacitors, which were provided by the Faculty of Chemistry of the University of Warsaw, where we added our solar cells and intermediate systems. So at this, we was said that we needed light solar chargers. So we also went to these directions, and we can make a solar charger which is of matchbox size, and the weight is almost 60 grams. And we have used various connectors between a solar charger and an energy storage, either BMS or step-up. So the efficiency is about 80% for with a step-up converter system. So it's a very good result, which allows this system to be applicable in practice. And the ideal solution, what is ideal solution? These are innovative light and hybrid solar chargers, where we have two types of energy storage. It's not really thought about it, but we have two energy storages, as you can see, so that the parameters are as we want. So a charger, it is fitted with a supercapacitor and lithium ionic batteries, can achieve higher instantaneous loads, and this can be used, for instance, for power supply of devices with large startup currents, for instance, electric motors. So we always want to use our experience in other scientific projects to be applied in next projects. As our Engineering Technology Institute, we specialize in camouflage for military applications. So we had made various projects. So the military equipment must be safe and reliable. We have developed two types of pixel camouflage, and it was using adequate parameters. We managed to observe, and you do not see it on this small picture. So we can show that these proposed solutions are good. Yes, they are good, and I would like to ask you, well, I have just 1 minute, but I will try. Here you can, well, I'm not sure. Can you find these hidden charges? They're here. It's really difficult to see. So this was a project which was completed thanks to NCBR, because we were co-financed, and very fast we can also do this flexible photovoltaics. This was a project with Lubava, where we can cut to size these photovoltaics mats, and they can be applicable in practice. So we can connect also energy storage to them. And on the left-hand side, I present light simulators, also designed in our institute, with dimensions 1.3 to 0.9 meters. If you want to have such large photovoltaic panels, it is possible. And to conclude, we have also solutions like this. So with our tailor-made devices, a hybrid system of energy storage, double solution, double application. So that was designed in our institute and implemented for our solutions in a military polygon and a set of laboratory energy storage designed in VT. So the number of bricks is decided by a customer. We have a special software for this, so it can be managed remotely and locally. And we also have renewable energy sources. We have additionally wind power. So these solutions were implemented in the military applications. On the left side, we will have mobile photovoltaic blocks. And to the end, it is my last slide. We have implemented hybrid dual solutions with a field solar power plant, which we used various transmission medias, internet channels, LAN, Wi-Fi, GMS of VMAX, and to the end, as VT specialists in implementation of photovoltaics for practical solutions for the military. So this TRL9, as you can see, apart from this field photovoltaics power plant, we also have other solutions. For instance, portable water treatment filter, which is powered by the solar power. It's very interesting. And just to end, we never have purely a clean electricity. Each energy production generates waste. So I would like to tell you about the waste and recycling of silicon photovoltaic cells is the future. Thank you very much for your attention.
Dziękujemy bardzo.
Thank you very much, Professor, for telling us about the activities of the WIT Institute and its successes, great successes in photovoltaics. In general, this is really impressive. And now I would like to ask Professor Jakub Ryś from the Jagiellonian University, who will give a paper, will present a paper on the modification of the guided meniscus method, new methods of creating thin layers for photovoltaic technology purposes. So thank you very much. I wanted to first thank you for inviting me to this conference here and for allowing me to present the results of our work that we conducted the New Materials Engineering Institute of the Jagiellonian University, and this is work focused on using new methods for producing thin layers for photovoltaic technologies. For many years I have been dealing with thin layers. I then moved on to the application of those thin layers in photovoltaic cells, and I will show you step by step how our work progressed and what we have managed to achieve so far. It has been mentioned today that the generations of photovoltaic panels, there are several cells, there are several generations. They can be produced of various materials. If you look at the 2+ generations, so all generations above 2, so 2 and higher, however many of them there are, those are cells that are produced of various materials, organic, inorganic. They may combine, the cells may combine two materials, but what is common for them is that they are thin layer systems. So to produce such cells, you have to learn how to produce thin layers. Of course, there are many methods of producing thin layers, very many methods. I have given you 2 examples. So deposition from the gas phase, chemical or physical. There are also methods such as wet methods, I would call them. So using various types of paste, so screen printing on the left, And then a method which for many, many years we have used at our lab, which is to produce organic cells. This is a very simple method. This is spin coating. And this is actually used in Polish, so I will continue using the term spin coating. So using spin coating is quite simple. You take two materials, donor and acceptors, you mix them in a solvent, then once you get a solution, you pour it on a rotating substrate, and when the substrate spins, you get a uniform layer on it. And we must have produced hundreds or thousands of such cells. So this method is really effective. But the problem with it is it's not scalable. You cannot imagine spinning at several thousand RPMs, spinning, let's say, a jumbo-sized plate of glass. That is just not realistic. But as we have seen at the first lecture, there is a need to produce cells on such large surfaces. So we have started looking for other methods or applying other methods. And the professor before me mentioned the blade method. So you use a blade to stretch or spread solution, similar to the one for spin coating and polymer solar cells. We have selected a slightly different version of this method, where instead of a sharp blade, we use a cylinder, and we drop a little bit of solution between that cylinder and the base. You are wasting less, because in the case of spin coating, over 90% of the material is flows off the surface, whereas here you can just spread the solution over the surface by dragging that surface below that meniscus. But that was not sufficient for us yet, so we tried to find a method that would allow us to control what we get better. The first idea we came up with was that we should add additional voltage. So let's apply voltage between the cylinder that is spreading the meniscus and the base. In solar cells, the base is a transparent electrode, so it will obviously conduct electricity. Does it work? If we use a polymer mix, then it works very well. By switching the voltage on and off, the voltage applied to the meniscus, we can dramatically change the morphology of that layer of the polymer mix. This was then also used for producing solar cells. As you can imagine, that was not sufficient for us, so we thought, what else can we change here? And as it turns out, we can add other factors that will allow us to influence the processes that lead to the final deposition of the thin layer on the base. So apart from voltage that I have already mentioned, we have also tried using light. So we're still planning to also use a heater that will actually be inserted into the cylinder, so we will be able to switch on and off certain reactions which are temperature sensitive, and a natural modification of the process by using a magnet. If the material that is being spread has magnetic properties. Today I just wanted to briefly show you two examples of using voltage and light to create such layers. So let's start with voltage that I have already mentioned. If the solution that we have between the roller and the base, if it doesn't conduct electricity, we can still use electrophoresis, and we can use it to modify the structure of the polymer layer, of a uniform polymer layer, which only contains one type of material. What I have shown you a moment ago is we can modify the morphology of the layers of a polymer mix. We can also, and this is used for DSSC cells, we can electrophoretically deposit dyes, which allow us to shorten the time of depositing dyes from 24 hours to, let's say, less than an hour. Another case, which I think is even more interesting, because maybe because of my background in organic electronics, those are phenomena that occur in solutions containing ions. So there is a lot of literature on electrochemistry, and we are using a lot of what has already been achieved in that field by trying to spread the meniscus over the entire surface of this base. What it gives us is we don't have to have great tubs to conduct the process in. And what does it allow us to achieve? Well, as an example, I want to mention platinum galvanizing. We have also produced layers of metals on other metals, but the most interesting thing for us is producing metal oxide layers on transparent electrodes. Why? Well, because if you remember the first and the second lectures, many solar cells start from having to apply a layer of, for example, titanium oxide or zinc oxide on this transparent electrode. There are many oxides that can be used. And yes, we can actually deposit such oxides. Here you have examples of zinc oxide deposition. You can see two sets of images from SEM and AFM microscopy. And what I want to draw your attention to is the fact that not only can we deposit those oxides on the surface, but by slightly modifying the contents of the solution from which they are deposited, we can dramatically change the morphology of those layers from agglomerates that you can see in the top pair of images to nanoflakes, which you can see in the bottom pair. And this has great impact on the catalytic properties of such materials, because if you have greater surface, then they can absorb much more, let's say, dyes or quantum dots that have already been mentioned. So we have checked that this method definitely allows you to produce layers of titanium oxide, molybdenum oxide, nickel oxides, but also molybdenum sulfide, two-dimensional material, very interesting. And in the context of photovoltaic cells, it's also very important the use of monomolecules of metallic platinum, which have very strong, which have great properties for photovoltaics, but also apart from photovoltaics, catalysis by platinum is used in many other applications. So if you were interested in more materials about this, there will be another speaker who will be speaking about this method, and in the poster session you can find the poster by Jakub Wilgocki, who will show you more details about this method. So if we're using about the use of light, then this meniscus should also contain a solution that is light sensitive. So we are mainly interested in depositing metals using this method, because then we would not need a conductive base. You could perform this reaction on a glass, directly on glass, or on transparent basis. So we have tried two variants. In one, we use a strong laser, well-focused laser beam, which allows us to very locally cause a photoreaction, and then you get something like a laser printer, a kind of wet laser printing of metallic pads on just about any surface. Another method uses a similar source of light, but this time it's not focused but dispersed, and as a result, we can coat the whole layer, the whole surface, with a more or less uniform layer of what is produced as a result of this photoreaction. To prove this, I'm showing you on the left a photograph of what the process of producing those parts looks like. So I hope you can see two thin darker lines on this piece of glass. They were produced by guided meniscus method using highly focused blue light. You can see the beam of the blue light here pretty well. This method allows us to produce silver parts. We can also produce gold parts and platinum parts, and this is because those materials are the most universally used for photovoltaic cells. Of course, the conductivity of those parts depends on how well the beam of light was focused, but since we're working in a liquid, we also have to consider diffusion. But in terms of the thicknesses of those parts, they can be hundreds of nanometers thick, so they actually have macroscopic conductivity. The second method, the method using dispersed light instead of focused light, so this dispersed light illuminates the entire surface of this meniscus, allows us to create in DSSC nanoparticles of platinum, which we actually deposited on the FTO. This is the counter electrode surface, and they have photocatalytic properties that can be even better than traditional platinum deposited from paste and then heat treated, so annealed. So here I can show you this method, and you can see the catalytic properties of the platinum deposited by the old method and by our method. If you were interested in any details, then please you will be able to hear them during the lecture of Mr. Dobczyński, who will present in the last session of this meeting today. So to summarize, the method that I have shown you allows us to deposit various materials. They can be metals, they can be metal oxides. As I said, the literature on electrode deposition is very broad, so we can use deposit many different materials using this method, and we can relatively easily modify the process of deposition by, for example, changing the composition of the solution. We can coat the whole surfaces, or we can coat them locally, so we can create various patterns, meaning print those patterns. And finally, what I started with, the problem of coating huge surfaces. Well, this method is scalable. We have produced a prototype at our lab, which allows us to move from the microscopic pieces of glass to plates of glass, which are let's say 50 centimeters in this case. But we could if we invested more, we can just have a longer meniscus, guided meniscus, and that would be enough. So I want to thank everybody who have done this work, because they are sitting in those labs and they are conducting all those experiments. And then I want to thank you for your attention. Thank you very much for this very interesting lecture and being disciplined in terms of time. And you said 50 centimeters on that last slide, so I imagine this huge shipyard gantry crane, traveling crane. So, you know, this shows that the breakthrough has already been achieved. It's just a question of moving from mobile phones sized like 2 bricks to today's ones that fit in your pocket. It's just, in this case, we are moving in the other direction. I want to invite Dr. Sławomir Wolski from the Rzeszów University of Technology, and we're once again moving to quants. So I just remember that there is only one thing from physics that I remember from school, that when we measure something, we're changing what is being measured. So I wonder how that applies to creating quantum dots, because if we measure where we place them, do we still know what they are? Thank you.
Well, when we're talking about the sizes, so the quantum dot is a macroscopic subject, so there's no problem with measuring it, so it does not change its location. So we can be sure where it is. But my presentation will be a continuation of will continue Dr. Kwasnicki's paper on the potential of quantum dot for increasing efficiency of perovskite cells, but not only them, because this part is related to a project which was completed in ML system and which was related to the quantum glass project, where at this initial stage of the project, we tested and we made a decision on various substrates on which we could implement quantum dots. And the team which tried to estimate this potential for increase of efficiency, there was Professor Dogayev from our university, Professor Michał Inglot who is present at this room, me, Wolski, and Mr. Paweł Kwaśnicki. And this team was also led by Professor Barnaś from Poznań of University of Evgeny Sherman from Bilbao, Spain. And that was the team that was the project team. And now I would like to emphasize that this presentation will be quite technical. I removed most of formulas, but so, ladies and gentlemen, as it was mentioned, this structure of absorber was selected by various methods. We have tried to estimate, was it possible to implement quantum dots on a perovskite substrate. Professor has mentioned perovskites, and these are breakthrough photovoltaic cells, mostly because of an increasing of a significant increase of efficiency of perovskite cells. You can see it on this graph, which is taken from the National Laboratory of Renewable Energy from the USA, and which monitors the development of renewable power. And here you can see with red dot an increase of perovskite cells from 13% to 23% in 2019. And another advantage of these cells is the fact that it can be easily produced, that can be simply printed, no high temperatures needed. And this gap is 1.76 electronvolts. And they are developed dynamically. They develop dynamically, and this increase of efficiency, the efficiency is growing really fast. So another advantage of the perovskite cells with regard to ML system, ML system is specialized in construction of photovoltaic systems which are integrated with buildings. Integration with buildings is related also with colors, and both dye cells and perovskite cells can be dyed and composed with the architecture. So when we are talking about the strategies for improving efficiency, we can have low energy and high energy cells. What does it mean? These materials, which are used for photovoltaic cells, these are usually semiconductors, and semiconductors have the energy gap, and to absorb a photon, the electrons from valence band go to conduction band. They are separated spatially, and they go on the external perimeter. So then we can say that if we have photons with energy higher than the energy gap, then the gap band gap, an electron can be excited. And then again, if we are talking about a higher energy, like ultraviolet, part of the energy is lost in the form of heat. So as we do not want to waste this heat, to lose this heat, we have the MEG effect, which is exciting of many electrons, and this part of energy is converted into releasing an electron from the structure. So the use of multi-junction structures, so the electron streams go through a multi-junction cell, and each of the junctions is adjusted to a different wavelength. So we have these absorptions for many wavelengths, and it is very similar for quantum dots, which are of various sizes, and it you could see the change of this gap depending on the size of a quantum dot. Also allows us to have absorptions of various wavelengths. And another strategy of reaching these photons from infrared, so low energy photons, which have energy under the gap. So here we have the multi-photon processes. Also, many photons is combined to release a single electron. So, or we use certain energy levels which are in this absorber gap. And it can be by implementing of quantum dots in the absorber. And it turns out that these semiconductor quantum dots are a very promising method for increasing the efficiency of photoelectric devices. So we have postulated this, so that these additional levels which appear in the gap, in the forbidden gap, they will extend the scope of frequencies towards infrared. So this here you can see a physical model, quantum well forming. But when we are talking about the geometric model, we have postulated that in the first approach we would have a two-dimensional model, and the quantum dot would be circular. Of course, it then can be converted into cylindrical. So these quantum dots which we have seen. So we can say that depending on the parameters of the electron parameters of a perovskite material, as you can see at the figure on the left hand side. So the first horizontal line from the top, this is the vacuum level, and from this vacuum level we can calculate this parameter. So for the perovskite we have the work of leaving, of exit, and when we implement quantum dots, we have electron affinity compared to the vacuum level, which corresponds to the level of conductance band for a quantum dot. And then we have conductance band and valence band. And in this structure, we can open, a quantum well can open in this structure because of electrons or because of electrons and holes, as for the second case. And the whole process of of determining energy levels is related to solution of a basic formula, which is a Schrödinger equation, and we can use it to determine energy levels which are formed here in this quantum well, which is related to a quantum dot. So this we have solved it as a function of, I will not quote these formulas, but I will show the results. So just to conclude, the energy structure is as shown on the left-hand side. The material is perovskite, and we have a quantum well of the depth of U0. And we have selected, for just a rough estimation, we have selected a few sets of quantum dots, ZNO, ZDS, ZNS, or gallium arsenic. So arsenide. So here you can see some parameters, physical parameters of these dots, and I think you will be interested in the graph which is shown here on the right-hand side. So let's have a look. We have energy levels which depend on the size of a quantum dot, and this quantum dot size here is in nanometers from 1 to 5 nanometers, and and note that as the size increases, the energy levels decrease. So quantum dots will have a certain distribution of sizes, and therefore these levels will not be really set for the whole matrix implemented with quantum dots, but these levels will be denser, and we have selected one size quantum dot. So we have, when we estimated this according to this simple model, energy levels for various materials are visible. You can see them here, and depending on the size and on the type of material constants, we have one or more levels, and this is an initial assumptions how to select the dots. And another aspect which was mentioned by Dr. Kwaśnicki, we also have a problem with absorption, for instance, of these dots on the substrate, but this is a different subject. We dealt with the absorption of photons in the quantum dot levels. So we have levels and energy levels, how they translate into the quantum absorption, into the photon absorption. Here, to calculate this absorption coefficient, we have used the Fermi rule, and let's have a look at the right-hand side graph. So note at the 1.6 electron volt level, we have the energy of a quantum, and this is the absorption edge related to the energy gap of perovskite, which is the main absorber. But note that even for a CDS dot up to 1.04 electron volts, it is possible to absorb the radiation. So this is quite a sizable. It is infrared. Also have a look at the units. So if we are talking about the intensity of the absorption, so we have arbitrary units which are shown only in terms of quality, not quantity. So the absorption effects in the perovskite layer will be much higher. So this is the case if we are talking about wavelengths. So let's have 4 graphs. This is still the same material, CDS, a quantum dot. On the left-hand side, we have 4 nanometers, and on the right-hand side, we have 8 nanometers. And at the top, this is described in terms of energy, at the bottom in terms of wavelengths. So once again, when we have a look at the bottom graph, the absorption is about 0.8 micrometers and up to 3. We can extend it up to beyond 3 in the quantum well, which forms as a result of implementing a quantum dot in the absorber material. And with regard, and now we have the absorption coefficient, but how it translates into the photocurrent, which is the parameter which is characteristic for a photocell. So this photocurrent is related to two competitive effects. The first one is generation of carriers, and the first formula which you can see is responsible for generation of carriers, which can result from changes from valence and conduction bands in perovskite, and these bands and the levels which are marked in colors and which are levels in the quantum well. So this discrete is the summary. The first part of this formula is discrete, and the other one is continuous. And the second competitive effect is recombination, and this is S to -1. And here we can also see the coefficients related to shifts from various between the levels from the conduction and valence band in perovskite. So here you can see some factors, some coefficients which are in these formulas, but the final result is this formula in the frame, which is, shows the photocurrent. So to have the photocurrent, these carriers which are generated by the light must go a certain way to the p-n junction and cannot recombine. So this is, we also tried to estimate this. Just 2 minutes. Good. I will try to make it. So you are the last, so you must make it in time. Okay, this is the result which you can see, and this top graph. Here we have generation of carriers. On the left-hand side, we have generation of in the valence band, and these are so these are holes, and on the right hand we have in the conduction band, and these are free electrons. And on one side we have the scale. We have carriers related to generation of interband generation, and on the right hand side we have generation. On the right-hand axis, we have generation between the levels and bands, and this interband generation is 6 times larger. For electrons, it's 4 times more. So we can say that 1,000 less doesn't matter for carrier generation, but this is only for discrete levels. And it turns out, and now I'm trying to sum it up, to wrap it up. For perovskite levels, we have additional levels of energy which extend the frequency scope to infrared. But as we do not have them to avoid strictly discrete levels, we need to expand them. So they naturally expand by scatter of quantum dot sizes, and by neighboring wave functions. So if we have 2 quantum dots next to each other, so these levels also extend, and we have extension of a level here, and depending on the distance of the quantum dots, it's falls exponentially, so very fast. And the third type of level extension, it's not really a method but an aspect. This is taking into account shape, but it's not just a two-dimensional model, but also the size in the vertical, in the perpendicular axis, because these dots are worm-like or a cylinder shape. And here we have additional energy levels, so this is extension of the level into the energy band. So, thank you very much for your attention. Thank you very much. And even I can say that this panel was very interesting, even though I did not understand everything. However, as we have the rule which has been applied, and each panel we can select the best, we can choose the best presenter. Because and I agree, because I understood this paper, and I agree. Mr. Paweł Kwaśnicki was the best, because I managed to understand his paper. So thank you very much. And I have noticed that for next panels we will have the same issue of quantums. So we'll discuss quantum dots. So I wish you very interesting and fruitful research. Thank you very much.
ML System. Zmieniamy świat dla przyszłych pokoleń. Natura to skarb. Przyszłe pokolenia cieszyły się światem, jaki znamy. Niezbędna jest transformacja energetyczna i my jesteśmy jej częścią. W Centrum Badawczo-Rozwojowym tworzymy innowacje w skali świata. W naszej fabryce produkujemy ogniwa, moduły fotowoltaiczne, systemy mocowań, szyby z powłokami kwantowymi, szyby, które świecą. Fotowoltaiczne żaluzje. Fotowoltaiczne fasady wentylowane. Fotowoltaiczne fasady. Fotowoltaiczne świetliki. Kolorowe moduły fotowoltaiczne. Rozwiązania Smart City.
Dzień dobry Państwu.
Dostarczamy kompletne rozwiązania systemów fotowoltaicznych zintegrowanych z budynkami. Szyby, które grzeją.
Dzień dobry Państwu. Czy mogę prosić o potwierdzenie, że jestem słyszana?
Które grzeją i ładują.
Halo, halo.
Szklane grzejniki. Szyby ze zmienną przeziernością. Chronimy zdrowie. Wirusobójcze przegrody szklane. UV-box. COVID-detektor.
Bardzo bym prosił. Dzień dobry Państwu. Czy jestem słyszany, czy Państwo mnie widzą?
I ograniczenia efektu cieplarnianego. ML System. Zmieniamy świat dla przyszłych pokoleń.
To chyba Państwo mnie nie słyszą. Pani profesor, czy Pani mnie słyszy?
Tak, słyszę. Czy Pan mnie też słyszy?
Ja Panią słyszę.
Dobrze, to czy jeszcze jedną rzecz jest możliwość wypróbowania, czy prezentacja się podłącza.
Niedługo PGE zmieni jego moc w zieloną energię.
Dobrze, tam Państwo...
Prost do Ciebie. PGE Polska Grupa Energetyczna. Moc bałtyckiego wiatru w Twoim domu.
Od tysiącleci człowiek odkrywa świat oraz mechanizmy nim rządzące.
Dobrze, tam widać, Państwo rozmawiają, Pani Profesor, czy Pani widzi tę prezentację?
Lepszego zrozumienia świata. Potrzebna jest do tego odwaga, która pozwala nam docierać tam, gdzie nikt wcześniej nie dotarł. I odpowiedzialność, która sprawia, że naszą wiedzę wykorzystujemy dla wspólnego dobra. Podstawowym obszarem naszej działalności jest wydobycie gazu ziemnego, ropy naftowej oraz sprzedaż tych surowców. Jesteśmy liderem rynku gazu w Polsce, notowanym na GPW. Działamy globalnie. Stale poszerzamy wiedzę, prowadzimy badania i inwestujemy w nowe technologie.
Panie Piotrze, czy może mnie Pan na sekundkę wpuścić, żeby zaczęła, czy się włączy prezentacja, dobrze?
Tak, już odszerowałem, więc...
Jesteśmy wiarygodnym i pewnym dostawcą do naszych partnerów biznesowych.
Okej, dobrze, czyli wszystko widać.
Gwarantujemy stałość dostaw.
Czy teraz jest dobrze?
Tak. Okej, teraz jest full screen w pełnej prezentacji, wszystko widać.
I stabilnego rozwoju.
Panie Piotrze, proszę powiedzieć, czy Pan widzi moją prezentację, czy nie mogę się wyłączyć, tak?
Tak. Aczkolwiek nie wiem, jaka jest kolejność prezentacji. Nazwiska chyba były tak dosyć losowo wymienione.
Chcąc dywersyfikować źródła pozyskiwania...
Pani Profesor, to jeszcze jedno pytanko. Czy mnie słychać z mojej strony jakichś trzasków czy szumu? Bo...
Nie, bardzo dobrze słychać Pana, ja tylko właśnie chcę zobaczyć, bo Pan zaczyna, potem jest Pan Grzegorz Łuka, potem ja i koniec.
...działań sprawia, że jesteśmy kluczowym gwarantem bezpieczeństwa energetycznego Polski. Gaz ziemny jest najlepszym rozwiązaniem dla każdego przedsiębiorstwa, które pragnie działać w zgodzie ze środowiskiem naturalnym. Wykorzystując zasoby ukryte w naszej ziemi, troszczymy się jednocześnie o przyszłe pokolenia. Naszym celem jest ciągły rozwój i dostarczanie efektywnych rozwiązań energetycznych. Dzięki temu jesteśmy dzisiaj obecni niemal w każdym polskim domu. PGNiG. Odkrywamy przyjazną energię.
Energia elektryczna towarzyszy nam w każdej chwili życia. Za stały i bezpieczny przesył energii elektrycznej w całej Polsce oraz bilansowanie krajowego systemu elektroenergetycznego odpowiadają pracownicy polskich sieci elektroenergetycznych. Energii elektrycznej nie da się przechowywać, dlatego w każdej chwili należy produkować jej dokładnie tyle, ile zostanie zużyte. Oszacowanie zapotrzebowania na energię elektryczną i jej bilansowanie to jedno z najtrudniejszych i najważniejszych wyzwań, z którymi polskie sieci elektroenergetyczne mierzą się każdego dnia. Nasza sieć to ponad 14 600 km linii 220 i 400 kV. Wraz z dynamicznym wzrostem zapotrzebowania na energię elektryczną rozwijamy sieć elektroenergetyczną, by sprostać wyzwaniom nadchodzącym w kolejnych dziesięcioleciach. Przy wszystkich naszych inwestycjach minimalizujemy wpływ na środowisko naturalne i otoczenie. Wspieramy społeczności lokalne i naszych sąsiadów. W naszych prognozach dotyczących zapotrzebowania i popytu uwzględniamy zmiany zachodzące na rynku energii. Wyprzedzamy je, aby zapewnić bezpieczeństwo energetyczne naszego kraju. Bierzemy aktywny udział w transformacji energetycznej Europy. Jesteśmy częścią jednolitego, zintegrowanego europejskiego rynku energii elektrycznej. Krajowy system elektroenergetyczny jest szczególnie ważny dla bezpieczeństwa państwa. Dlatego przykładamy ogromną wagę do fizycznej ochrony naszej infrastruktury i cyberbezpieczeństwa systemów. Polskie sieci elektroenergetyczne realnie wpływają na polską gospodarkę. Polskie sieci elektroenergetyczne. Energia w dobrych rękach.
Życie to energia. Być może nie zastanawiałeś się, skąd się bierze. Jaką drogę musi przejść. Ale dzięki nam masz pewność, że zawsze będzie tam, gdzie jej potrzebujesz. Już od ponad 15 lat Gaz System zarządza siecią przesyłową w Polsce. Zapewniamy bezpieczeństwo i ciągłość dostaw. Co roku przesyłamy miliardy metrów sześciennych gazu. Stale rozwijamy się, budując tysiące kilometrów nowych gazociągów. Współtworzymy zintegrowane systemy przesyłowe w Europie, dzięki takim projektom jak dwukierunkowy gazociąg łączący Polskę i Danię, korytarz północ-południe czy interkonektory. Będąc filarem bezpieczeństwa energetycznego kraju i regionu, rozwijamy inwestycje umożliwiające dostawy gazu z nowych źródeł i kierunków. Rozbudowujemy terminal LNG w Świnoujściu. Jesteśmy też odpowiedzialni za powstanie terminalu pływającego w Zatoce Gdańskiej. Zatrudniamy ponad 3000 pracowników, których łączy pasja i profesjonalizm w dostarczaniu czystej, konkurencyjnej cenowo stabilnej energii. Dążymy do zrównoważonego rozwoju, wspierając lokalne społeczności i chroniąc środowisko. A ponad wszystko zmieniamy oblicze polskiego gazownictwa oraz integrujemy rynek gazu w Europie. Gaz System. System, który łączy.
Jeden test. Masz całość, ok. No i tutaj powinno ci się też pokazać po selekcie. Ok, w porządku.
Jako narodowy operator systemu dystrybucyjnego i europejski lider tej branży przez prawie 200 000 kilometrów gazociągów.
To jest dwójeczka. To poprawy będziesz miał.
Stale czuwamy nad bezpieczeństwem i ciągłością jego dostaw. Chcemy, by z błękitnego paliwa korzystało jeszcze więcej mieszkańców Polski. Dlatego realizujemy strategiczny program rozbudowy infrastruktury dystrybucyjnej.
Inwestujemy w tworzenie nowych gazociągów, rozwijamy nowoczesne technologie i podnosimy efektywność podejmowanych działań.
Stawiamy także na gazyfikację wyspową. Dzięki stacjom regazyfikacji skroplonego gazu LNG zapewniamy szybki i bezpieczny dostęp do tego paliwa tam, gdzie go wcześniej nie było. Dzięki naszym działaniom wzrasta liczba odbiorców gazu, a proces przyłączenia do sieci dystrybucyjnej PSG jest łatwiejszy niż kiedykolwiek wcześniej.
Wystarczy zgłosić się do jednego z prawie 200 miejsc obsługi klienta w całym kraju lub skorzystać z internetowego portalu przyłączeniowego.
Zaczyna się, nie musi.
Nie mamy symultana.
Aha,
a musi być. Musi. Bo leci na kanał angielski.
No to jak już tam...
Dobrze, czy pan, panie moderatorze, może już siadać?
Dobra.
Ale nie wiem, gdzie jest pan...
To taki dziwny panel będzie, nie? Bo będziemy mieć dwie osoby na online.
Czy ja mogę poinformować, chociaż napisać na Zoomie, bo ja nie mam czatu, ja nie mam tego Zooma, nie wiem, gdzie on jest, na którym monitorze. Że będzie słyszał, czekają, bo już nie wiedzą, co się dzieje.
Możesz sobie czat przeciągnąć na tą stronę?
A on jest, a to jest full,
Już
polski, tak?
To jest full screen. Teraz masz czat.
Gdzie to jest? To jest to, gdzie to? No bo jak wchodzę w meetings, to jest tam. A ja potrzebuję napisać. Albo coś takiego. Ja też nie wiem, bo oni nas słyszą tutaj. Cały czas lecą reklamy.
Dzień dobry Państwu, cały czas Państwa słyszymy, nie wiem czy Państwo mnie słyszą.
Pytam, czy nas słyszy. Musimy coś powiedzieć. Ja nie wiem gdzie macie wejść.
Ja się na przykład pojawić tutaj?
Tak, proszę siadać. Już zaczynamy.
Ale to proszę,
żeby im powiedzieć. Nie wiem do czego mówicie.
Mikrofonu proszę dać dźwięk.
Raz. Słychać mnie? Raz. Słychać mnie? Zdalnie?
Tak, słyszymy Pana.
Przepraszam.
Proszę jeszcze coś powiedzieć.
Dzień dobry Państwu, czy Pan mnie słyszy?
Jeszcze, proszę cały czas.
1, 2, 3, 4, 5.
O, dziękuję bardzo, dziękuję. I jeszcze troszeczkę.
Dobrze, słyszą nas.
Dobra. Do góry włączamy. To będzie teraz Pani Mary i Pan Piotr.
Czyli zdalnie.
Tak, zdalnie oni udostępniają ekran. Co tak mi się wydaje.
Z prezentacjami jeszcze oni tam
Tak się zgadza.
Szanowni Państwo tam wysyłali do ostatnich chwil, także nie wiem, czy się udało wszystkie wyjaśnić. Jak nie, no to też.
Prezentacje oni mają tu?
Nie.
Nie, będziemy włączać sami.
Dobrze, nie przy...
Aż tak dobrze mnie słychać?
Tak.
Bardzo dobrze.
Dzień dobry.
Dzień dobry.
To co, minuta wchodzimy?
Dzień dobry Pani Profesor.
Z mojej strony to...
Nas widać i słychać też, tak Pani Profesor?
Słychać, znaczy widać to nie widzimy, bo widzimy
Aha, jeszcze nie.
jakąś...
Ale słychać dobrze. I pan doktor.
Tak.
Łukasz. Czyli przedstawiciel systemu. To będą kraje?
Tak. Ja zrozumiałem po angielsku, bo myślałem, że to będzie po angielsku.
Nie, tłumaczyłem. Fajnie, ale po polsku.
To co ja mam?
Nie, właśnie.
Mam zmniejszyć czy podnieść?
Delikatnie może było podnosić. A jeszcze pan Wróbel. A jest pan Wróbel? Pan doktor? Czy pan doktor Wróbel jest z nami już?
Dzień dobry, tak, słyszę Państwa, jest mi obecna.
Tak, dzień dobry panie doktorze.
Dzień dobry.
Uniwersytet Warszawski, tak? Panie doktorze? Dobrze.
Tak jest, zgadza
A
się.
pani profesor również?
Także.
Dobrze, to potwierdzamy afiliację, bo było trochę...
Parę pokoi dalej.
Tak.
Nawet wydział ten sam.
Czyli to, możemy zaczynać?
Leci reklama, macie Państwo
Aha.
43 sekundy.
Dobrze. No ja po prostu Państwa przedstawię pokrótce.
So I'll just introduce the speakers briefly and hand over to them. So we've got Dr. Piotr Wróbel. I don't know if you would like to start. But my question is, how much time have I got? Have we got any? Has there been any change? We've got 1 hour for this until 11:45. So maybe 15 minutes for the presentation and